Okay, good afternoon, everyone. Welcome to TAPO Seminar Series 58 and talk number 5. And today we have Dr. Sikarin to tell us about from England to Einstein, statistical origins of the relativistic Lagrangian and Hamiltonian. Please welcome us.
All right, okay. Thank you very much. I think the microphone is working, right? Okay. Please wait. I think so, yeah. Okay. Anyway, so today I'm going to talk about this title. And I put this picture. Yeah, of course, it's a bit fancy, but I hope that this could capture the essence of the talk. And let's see. We're going to, well, maybe come back to this picture again at the very end. Okay. So this talk is based on this paper, which is actually a joint work with my former master student at KMUTT and a former postdoc at the IF Assoc. Yeah, this guy. Okay, anyway. All right, so this is the plan of the talk for today. I'm going to start with the structure of physics theories. And then I'm going to explain about, well, briefly about multiplicative Lagrangians. And then I explain the process that I call emergent process, that how can we get relativistic Hamiltonian and Lagrangian from the Newton one. And I give you a conclusion as well as the open questions at the very end. All right. Okay. So here is the structure. According to my opinion, you might have different view on this kind of structure. At the bottom line, I put all the classical theory, but not all of them. I hope that could be contain all most of them. Okay. And in the second line, so you get something extra like quantum mechanics, quantum statistical mechanics, special relativity, something like that, which is like a top up another layer, right? And you can going up to the higher theory, right? Like a quantum field theory or general relativity, as well as a cosmology. And the quest is how to construct the quantum gravity. We don't know yet how to get that. And at the very top, I put the TOE, theory of everything, which is, again, we don't know what kind of theory we're going to get. That we wait and then we will see. And I put here in between because we don't know, it might be something else before that we could get into this kind of TOE. And for this part, I put here this kind of, because we have this kind of knowledge, somehow we can apply all this knowledge to explain some kind of phenomena in biology, chemistry, as well as in engineering. Okay, so today talk, I'm going to focus on this particular yellow lines, like this from classical mechanics to get special relativity, and as well as a bit on general relativity. Okay. All right, so we start with here at the bottom line. So we have Newtonian mechanics, which is actually we working with the equation of motion, which is nothing like F is proportional to the acceleration of the body, right? And we have like Gaussian transformation, right? And then we have space and time separately, I would say. And then we move up to the electromagnetism, and we find out that actually this kind of Gaussian transform doesn't work with this kind of equation. Then we need a new version of the transformation to make physics invariance, right, between the two initial observer, right? So then, oops, sorry. Okay, so then we have a better version we call relativistic mechanics, right? And then we have a new kind of transformation we call Lorentz transformation, right? With this gamma factor here. And the interesting point that when we get to this upper level here, then space and time now fuse to be one entity that we call space-time, right? And we get that kind of structure that normally we put this in the Minkowski space, right? Somehow, okay. All right. So and normally we know that under the appropriate limit, right? We could get from the upper layer to the lower one here. So the question is that, oh no, sorry, is, okay, that is kind of a top-down perspective that we have in physics, I would say. But not only the top-down perspective that we have in physics, we also have the bottom-up perspective that we have in the context of thermodynamics and statistical mechanics, right? Because this kind of, I would say, this is kind of bottom-up perspective because we could not keep track of the dynamics of each of the particle in the system, right? The thing that we do is kind of you look into the system as a whole, right? And you somehow, I put here is like you do some kind of average thing, and then you will get some kind of macroscopic quantity out of it at the very end, right? This is kind of bottom-up perspective. So, yeah. So the question is that is it so? The question that we have in mind is it possible that we can that we start from this the lower layer here, the bottom layer here, and then we go up to the upper layer? That is the quest for this work, actually. And let's see. So to do that, so we start with this paper. We should actually we construct a new type of Lagrangian we call multiplicative form of Lagrangian. And before we go to the new one, I'm going to talk about the standard one first. The standard one, the Lagrangian is nothing but the difference between the kinetic energy and the potential one, right? This is the standard form. And this one produced the equation of motion that actually we get from the Newton one. And you know that according to the non-uniqueness theorem, property of, I would say property of the Lagrangian, you can modify your Lagrangian by add like a total derivative terms, or you can add a constant, or you can multiply, or you can scaling your Lagrangian, right? You still get the same equation of motion. That's what we kind of knew, right? I put this type of traditional framework here, okay? And so the question is that we were asking, right? Are there alternative form of the Lagrangian functions apart from different between the kinetic and the potential one? And we find out that actually at least there is one form that we knew actually we solve in this particular work they call multiplicative one, right? Here. Okay, so we start with this particular form of the Lagrangian we call the multiplicative one, because there is a function of f which is actually a function of x dot and another one we call g, and this f and g must be determined, right? And I put here is 1 plus 1 space-time because we have one parameter x and one parameter time, right? That's why I call 1 plus 1 space and time. And in order to solve or to determine f and g, we just put it out back into the Euler-Lagrange equation, and I would say we do the reverse engineering, right? In order to get the form of the L. And according, and we also put the constraint that actually once we put this L into this Euler-Lagrange is going to produce this equation of motion. And then we can solve for f and g, and it turned out to be this one. And this kind of new type of Lagrangian come with the extra parameter here that we call lambda here. Okay, and the lambda is a dimension of the velocity here. And if we take the limit on the lambda, then we get the standard Lagrangian one here, according to this limit. And very interesting point, you can look at this Lagrangian as a generating function, I would say, maybe. Actually, if you expand this Lagrangian with respect to m lambda square, so you will get this hierarchy, infinite hierarchy of the Lagrangians, I would say, and all of them produce the same equation of motion. Okay. Okay, so I put this, the whole thing as an unconventional framework. Okay. And of course that we can work out what is a multiplicative Hamiltonian as well. You can apply, once you get this L lambda, you can apply the Lagrangian transformation, and then you can get this new Hamiltonian with the parameter lambda, which is actually in the form of exponential one. Okay, and according to this limit, you can get the standard Hamiltonian back here. And if you don't do this limit, you expand this Hamiltonian with respect to m lambda square, you will get as for the hierarchy of the Hamiltonian, which is actually all of them produce the same equation of motion. Okay. Okay. So here, this is like a side note, which is actually I got is from the stack exchange, which is actually that was supposed on the stack exchange. The question associated with this type of Lagrangian, which is actually there is a question from the Goldstein textbook, right? And also in a David Tong lecture note about this kind of Lagrangian is going to produce the same equation of motion. Then everyone just wonder how to construct this kind of Lagrangian, because nobody know how one could get this kind of Lagrangian. And if you look at the form carefully, it's nothing but is the second one in our hierarchy here, right? So I also wonder as well about this, how to get this Lagrangian, because I'm also look at the book of the Goldstein, and here this one, and unfortunately I could not email to him. I cannot send email to the Goldstein. They have sent email to the David Tong, ask him about how to construct this Lagrangian, and he's very nice, and he's answered my email. And he mentioned that it's kind of he get it from his colleague long time ago, something like that. And then anyway, that's the side story anyway. Okay, so now we're going to do a metric. All right. Sorry. Okay. So we noticed that actually we can swap the size of the lambda, and then you get this Lagrangian, and still produce the same equation of motion. I mean, yeah. Then you have the factor here as well. All right. And we're going to start to consider the first for the free particle case. For the free particle case, so you get this kind of Lagrangian, which it actually give you this equation of motion. Together with factor, we are not going to throw this factor away. We keep it, right? And this is the Hamiltonian one. And then what we're going to do next, we rescale the parameter to be like a beta lambda here, right? And then we get new Lagrangian and the Hamiltonian one. And after rescaling the parameter, you still get more or less, actually not more or less, exactly the same equation motion, but with a new kind of factor here, right? That's what we have here. You still need to keep the factor here. And next, what we're going to do is we're going to introduce this kind of distribution, right? Which is actually you can construct this distribution from the ratio of the Hamiltonian in this way. And we find out that actually this kind of distribution is normalized, right? You can check it. And then the next step that we do is you're going to look on the average of this L beta lambda with this kind of distribution. And it turned out to be this one. I mean, the result after you do this kind of average here. And if you pick lambda to be this c squared over 2, where this one is nothing but the relativistic Lagrangian here. That's it here. And so we get we get kind of relativistic version of the Lagrangian from the Newtonian one, I would say. But the Newtonian one is kind of not the standard one, and okay, you need more than the standard one to get to go on the process like I explained here. Anyway, we can do the same with the Hamiltonian. With the Hamiltonian, you can as well do the average here with this kind of distribution, and you get this mc squared gamma, and you can pick lambda to be c squared over 2, you get the relativistic Hamiltonian, right? Okay. So now we take a closer look here. What we did is somehow if you expand thing, right, in this way, and you put thing into the bracket, right? And you can see that actually what we get is kind of sum over possible statistical average of the Lagrangians in the hierarchy, right? Because yeah. And we need this, the first one, is even is the constant is very important piece, because otherwise you cannot put it back into into this night form here, right? So in this sense, so we have a view that actually is might relate to like an emergent phenomenon here, like this is I get from the internet, like a macroscopic behavior or the property that arise from the interaction of many simple components in the system that cannot be easily predicted or explained from the property of those individual components alone somehow, something like that. And then we put this kind of view on this kind of process because we look at the average of every single Lagrangian in the hierarchy, right? And then you get this relativistic one here, okay? Anyway, so I put the cartoon version to make it more accessible, I hope. So, so I start with this L lambda. As I mentioned, you can think this is like a generating function that actually give you this kind of a collection of Lagrangians here, as well as this constant as well, right? And then, so you explain the Newtonian, the way that we do here is mean that we rescaling the parameter, right? We do something a little bit with the parameter, and then we put all the Lagrangian in the tray, which is actually I portray the tray as the distribution, right? And then so I check it somehow, and then after you check it, the pattern will emerge somehow here. So this is like a cartoon version. So you will get this kind of relativistic version of Lagrangian from those kind of set of non-relativistic Lagrangians. Okay. Right. This is what we have, well, actually not what, but I try to make it simple, okay? So this is kind of, I have to say again, this is for the free particle case. The question, if we what will happen if we include the potential one, right? So let's see next. Now we're going to put back the potential, right, into the Lagrangian. And here we get the Hamiltonian with the potential as well. And we find out that actually the distribution is going to be exactly the same as the previous one, right, this one. And we're going to do this more or less the same process that we did. We do the average of this new Lagrangian, right? I mean L beta lambda with the potential one, and then we get this, I would call L tilde lambda here. Okay, and we get also as a Hamiltonian tilde here, right? And these two, I mean this new Lagrangian and this new Hamiltonian going to give you, again, the same equation of motion with the different factor here, right? It means that I put the word bow here because we find out that actually there is another way to write the Lagrangian and still give you the equation of motion, right, from the Newtonian one, right? Okay, and so okay, let's capture what we have before so far. Sorry, so we start with the standard one, right? You get this equation of motion, and then I mentioned that actually we can construct the multiplicative Lagrangian, right? And this is going to produce you more not exactly the same, but this equation of motion with the factor, right? With the factor in it, and according to the process that actually we do the average here, the average thing, then you get a new form of Lagrangian, yeah. And this new one, I don't know what it is yet, still give you this kind of equation of motion. And if you expand it, I mean, if you do like a silly expansion, you will get infinite hierarchy again, which is actually this is a new hierarchy, and you can see that the first Lagrangian, which is actually they are exactly the same, but from the second one they start to look differently. I mean, at least in terms of polynomial anyway. But anyway, all of them, I mean, all of them in this hierarchy and all of them in this hierarchy, they're going to give you this equation of motion anyway. Every single of them, all right? Okay, so now we kind of have plenty of ways, I would say, that you can write your Lagrangian that still produce the same equation of motion. Okay. Okay, now we look at the action. The action, so this is the standard one. We start again from the free particle case. Yeah. And this is the standard action. And this is, I would say, this is the non-standard action with the multiplicative Lagrangian right here. And I do expansion here, which is nothing but this is, I just want to emphasize that actually this one is the standard action, which it actually contains is the infinite hierarchy, infinite series here, right? And what we're going to do is the same trick that we did before. We do the average, right, with respect to this kind of distribution. After that, we finish the averaging thing, so it turned out to be this kind of action, and we can this is nothing but relativistic action, and this d tau you can put in this way, and then you get this kind of ds square. I mean the interval in the 1 + 1 Minkowski space. The thing here is that before here at at the upper level here, the parameter t is independent variable. And after you go through this kind of process, and then when you finish, now your t become kind of the coordinate parameter, which is a bit weird, but I don't know. But the math guide us kind of this way. We don't know yet what really happened with the time variable in this process, but what we get from the math is in this way. Okay. All right. So now, if we put back the potential into the action, we get this one. I mean, after we do the average thing, all right? Okay, so with this kind of factor, and then we kind of rescaling a little bit, so you get kind of the ds square in this way, right here. And you do further rescaling thing, you will get ds square in this form, which should actually look a bit familiar, but not really exactly the same, I believe. And well, because we now dealing with the case of 1+1 spacetime, I mean, if I understand correctly, the curvature tensor vanish, right, in this situation. So next we're going to compute only the Gaussian curvature. And then if we compute the curvature, then we need to work out all this kind of thing. And then we find out that actually the curvature, I mean the Gaussian curvature, I mean for this situation, depends on, well, it can be expressed in this way, right here, which it actually depends on the potential function in your Lagrangian, right here. And so if you expand your, your ds square bit by this condition, where you will get this form, which is actually more or less the same, the same one that actually we have in the case of you have the particle is located far away from the stationary source, right? Yeah. Which is very interesting, but we don't know yet. But this is the math that we get here. All right. So again, so this is cartoon version. We do the same with the action, and then we space, rescaling it, and then we shake it, and you get kind of the action out of thing of the process here. And the thing is that in the process, as I mentioned, at the beginning, space and time they are separated, right? And after we finish the process, they are fused to be one entity. Yeah, that is the thing. And then, well, we come to the conclusion. So in this kind of, I would say, new perspective, I would compare to the fog of the birds here. And we have a fog of the Lagrangians. And in this, they exhibit kind of pattern, right? And in this slide, they exhibit not pattern, but this kind of the relativistic kind of thing, right here. That kind of my analogy. You might not like it, but well, this is my analogy anyway. Okay. Okay, and then so now come to the open questions. So actually, this kind of question we get from the Lefferley actually. How does the choice of the distribution determine the transition from the classical to relativistic mechanics, or how does the different choice affect the result? I mean, if you change the distribution, what will happen? Like the box here to be like this here. We don't have that kind of clear answer yet, but I believe, I don't know. I don't want to say a thing now. We need further investigation. Anyway, and as I mentioned earlier, the role of the time in this process is a bit weird because at the beginning, there is the time is nothing but independent variable. After you finish the process, it's become like a coordinate variable. We don't know what really happened with the time variable. But I believe that if we could get like how to construct the Lorentz transformation from the Galilean transformation through this kind of statistical average here, we might gain a better understanding of the rule of time, because so far we don't have that kind of process yet for how to construct the Lorentz transformation from the Galilean transformation. We don't have that one yet. Anyway, and the next one, can we consider 2D Lorentzian manifold as an emergent thing from 1 plus 1 Euclidean manifold? We don't know. It might be, yeah. And so, in order to get like a more complete picture, we need, of course, 3 plus 1, right? 3 space and 1 time. So it means, so far we start with 1 plus 1. So we need to extend this kind of multiplicative Lagrangian into this kind of situation. But we don't know how to construct this kind of form yet. We don't succeed yet. It seems to be simple, but in the process, I mean, in the inverse engineering process, it's very difficult, because you cannot, you need to apply the separable technique, that kind of thing. It doesn't work for multi-variable here in this situation. Anyway, we don't have that this kind of Lagrangian yet. If we could get this Lagrangian, it might give us more insight about this process. Okay, and so there is a work that actually I work with the student from Newtonian University. Actually, we start with multiplicative Hamiltonian, and we can derive the solid entropy to the framework of statistical mechanics, right? From like you start from the ensemble that actually define on phase space, and then finally you get the solid entropy. Now we get a new Hamiltonian here. So it would be natural to ask what kind of entropy that actually related to this kind of new Hamiltonian. That is the question that I put here. Okay. And so this is not related to this particular work, but well, it's just coming to my mind. The Hilbert-6 problem, right? That actually mentioned about mathematical treatment of the axiom in physics somehow. Well, I think you probably know about this Hilbert problems, right? Yeah. I would say that he want to formulate. I believe that in mathematics, right? You start with the axiom, right, and then you can do things from that, right? That Hilbert view, he might probably want that actually. In physics, we should have this kind of a set of axiom or a set of basic equation, and then you can build up everything from that as well, I believe. Okay. So like you have like a microscopic thing here, and then you can build up macroscopic thing somehow. But well, there was partially success to prove this kind of problem. In order to formulate the axiom of the probability, I believe there was a work by a Russian guy. I could not remember his name anyway. And recently there was a work by a group of people that actually they can construct now the Stokes equation from the set of point particle somehow, I think. But I don't know the situation of that work so far. Okay, so now I think this kind of question extend to the field of quantum mechanics and also general relativity as well. But it might, well, you might say that actually, like in quantum mechanics, you could have like a set of axiom, right? And you can build up quantum mechanic thing, blah, blah, blah. But what I have in mind is that normally that actually we have kind of quantum mechanics up here, and you take a limit, right? And you get the classical mechanic back. The question is that, is it possible to go up from the bottom line to the upper line? I think there was attempts to construct quantum mechanics from the classical ones by, like, you start from the Newton equation, and you may put some kind of stochastic distribution to make it more probabilistic, something like that. But it was not, I think it wasn't success yet, because you might get something interesting, but you cannot get everything in quantum mechanics. That is the question. It might be possible, I don't know. That's it for my talk today. Yeah.
Any questions?
Thank you for a very good and interesting talk. I have a question about the distribution.
Yep.
So this is going to be a long question. Let me think about it. So, okay, you said that you pick a family of Lagrangian, right? And then you integrate that family of Lagrangian with respect to this distribution, and you get the relativistic Lagrangian. So my question is that, is it possible that the family of Lagrangian that you pick is universal in the sense that Fourier transform is universal? Like you can put any function and then transform it into integral of like sine and cosine with some respect to some distribution. So with this family of Lagrangian, you can also transform any Lagrangian to your family of Lagrangian with your choice of distribution as well. Like the family is universal. So you can put any function and just by tweaking row, you can get that function.
Yeah, very interesting. Interesting. You mean, let's say a cartoon here? You mean universal for this kind of thing?
Yeah. Right. So let's say instead of L, you put sine and cosine there, right? Okay. And then you can just tweak the row and you can get any function you want. So is L also like sine and cosine in that case?
Yeah, I don't know. It might be. Yes. Sine, cosine. Yeah, I don't know.
So you are thinking of the family of L as basis, or Fourier basis, and that row is just the function that are going to transform.
That's right. That's what I'm wondering. Like, could it be that L is just like the basis of that?
Interesting. I never think this kind of way before. It might be. I don't know. It might be. You can think this is like a. I kind of get your point. But I can't give you yes or no now. But thank you very much for this kind of new point of view. Very interesting.
I think it would be worth to investigate.
Yeah.
So just some small questions. So each of your Lagrangian is invariant under Galilean transformation. Right? L1, L2, L3.
I could. You mean this one, right?
Yes. Yeah, the L1, L2, L3, and so on. Each of them.
Well, we even L1 we don't know how to. Is it invariant? I mean, for L1.
I'm not sure. Have never really tried.
But I think.
But in principle, it should, right?
Yeah. Yeah, I think it's at this ELM level. I'm pretty sure that it's invariant, but I'm not sure. For the L1 is, I think it's going to give you extra terms, but once you put into the action, that extra term is going to be the total derivative. And it doesn't contribute to the equation of motion, I believe.
Okay. Yeah, and for the Galilean, so I think it needs to be for free particles, right? Just only free particles.
Is it? I don't think so. Is it only for the free particle? I don't think it should be applicable for any situation, right?
Okay.
I'm not sure. What do you mean by free particle?
I mean, when potential is zero.
Oh. Why is that? Because you could have two different initial observer, right? Actually observe the particle that actually accelerated, right? That these two observers should agree that actually this particle have the same, exhibit the same physics somehow, right? It's not necessary to be the free particle, right? It's good. Well, your particle can be under some kind of force, external force somehow. But according to the viewpoint of two different inertial observer, they should agree on the same physics.
No. Maybe I was just confused. Yeah. Yeah. It should be okay.
The Lorentz force.
Okay, but here as long as the potential is not velocity dependent, then yeah, maybe that there is truly the Galilean transformation, and as you mentioned, that is really interesting, right? That for each of them, yeah, suppose that they have Galilean, Galilean invariant up to some total derivative. Somehow the average is Lorentz invariant. And by the way, on this slide, I think L2 tilde is just basically the same as L2 up to some constant, overall constant.
Maybe, yes. Possibly, yes. Yeah, maybe.
Yeah, and maybe L3 as well. I don't know.
Yeah, if L2 is the same with L2, then the rest should be the same up to some scaling factor, right?
Yeah, because your L tilde, the top one is basically the second L.
You mean this one?
Yes, that one. How do you get it again? How do you obtain this Lagrangian again?
I mean this one, right?
Yes.
Okay. We get from this kind of average again. Okay. From this one with this distribution, right? And after we do the integrating things out, and is turn out to be this, this out.
So I think it could be sensible to expect
Yeah.
that the Ln and L tilde n would be like
Yeah, I think so. Yeah, because actually for the H we get the same hierarchy. That is actually you should get the same L, the set of L. Yeah, different scaling factor. Yeah, of course. Yeah.
Yeah, and another thing is that you compute the Ricci scalar.
Oh yes.
Well,
You mean-
I haven't really computed myself, but I have heard that in 2 dimensions there is no gravity. I don't know if how this is.
Oh
related
yes, yeah.
to
Because
the-
I just mentioned that actually, well, in this 2 dimension we cannot compute. The Einstein tensor, right? But what we did here, we just compute the Gaussian curvature, kind of. I think.
So it still have the Ricci
Yeah.
scalar.
Yeah, in order to get this kind of kappa here, I think. But for the, yeah.
Okay.
Okay.
Thanks.
Maybe Hong could help
Oh,
us.
do you know this? I mean, in 2 dimensions, yeah. No, just 2-dimensional space-time. Do they have the Ricci scalar? You don't. Yeah. How about 2 spheres? Two sphere has. But in here, it's space-time. So.
Yeah.
I mean, for 2-dimension Ricci scalar, I believe it's topological invariant. I mean, it depends, in alpha depends on geometry, such that it depends only on topology. I'm not sure about.
I believe this somehow is kind of intrinsic curvature of
Yeah. And all that it should be invariant.
Yeah.
Under whatever field inside. Because what I know is that the curvature, I mean, like the Ricci scalar intuitively is constant. It not depends on the geometry of the space, that it depends only on the topology that have holes or boundaries or something like that. So such that if you go forward your calculation, here you will be able to have the answer here. And if it's true that it is topological invariant, so it should be constant. So that would mean something I don't know.
Yeah, it should be, yeah. Because it's kind of intrinsic curvature of the, it should be.
If you require it to be constant, it should give you some, I don't know, maybe for later analysis.
Maybe, yes, of course.
You maybe for some constraint in your R.
Maybe, sure, yeah, of course, yes. Yes, yeah, maybe. It should be.
Can I ask like the primary motivation on how can you get the rho beta at the first place? You mentioned that if we have rho beta in this case, you would have the average to get the relativistic version of the Lagrangian. Can I ask you how can you get that in first place? Like motivationally?
You mean this one, right? Actually, at the beginning, we get different one.
Okay.
And to get that one, we start from this. We just naively look at this, the form of the Lagrangian, and we just do the scaling, the parameter. I mean, the parameter lambda, and we just is actually is not my insight. It's my student insight. Actually, he starts from just styling it on this Lagrangian, and he realized that if we multiply this Lagrangian with like a Gaussian distribution somehow, and then he can integrate. Oh, sorry, we can do the integrate out somehow the Gaussian, right? And then it turned out to be like you can get a nice forms, a closed form. After that what he told me at the beginning, and later we realized that if we put this kind of thing in the paper, actually we just studying it, and then we just realize that we multiply the kind of exponential Gaussian thing and then integrate out, then it might be not really kind of maybe a good reason. Then we try to look in another way that actually we can construct a new row here, actually related to the ratio of the Hamiltonian, and you still get the same relativistic Lagrangian. Well, yeah, I don't know. Is it answer your question?
Because I think it's very interesting because this particular function is kind of particular.
Yes.
I mean, the sense that it give you like. I just wonder, like, the first motivation. Are you working backward, or maybe it's solving that if you have the row and expectation value and give you the relativistic version, or I mean, do you solve it backwardly, or do you just put it in here and compute it?
I would say we just got it by accidentally got it. Coincidence kind of guy.
Yeah, but
it's kind of
but I can
surprising,
see that you start from like the normal distribution, and,
Yes.
and maybe you just deviate it, like
Yeah.
modify it in
Yeah,
a certain
sure.
way, and surprisingly, it give you interesting physics, interesting object.
Yeah, sure. Because if you remember, I mentioned about this kind of work at the group meeting, right? The organizer maybe couple months ago, maybe more than 2 months ago. That actually in that talk I mentioned about a bell curve distribution, right? If I remember correctly, and then we perform this kind of the same trick, and then we get the relativistic Lagrangian, and then we later realized that we somehow get this kind of new law actually related to this kind of ratio. And then we decide that actually we put this kind of thing into the paper. It might be maybe a good motivation that actually we can somehow this kind of distribution more or less relate to the ratio of the Hamiltonian somehow. Is kind of, but yeah, that at the beginning it's just there is nothing special. We just get it from by just looking at the equation. Yeah.
Okay. So the normal distribution would give the same answer?
Yeah, sure.
Oh,
this one and the bell curve one, give us exactly the same relativistic Lagrangian.
Oh.
But it has to be careful a little bit, because there was a different kind of rescaling parameter trick along the way. That kind of thing that happened. If you shoot different distribution, you need to perform different trick of rescaling thing. Right? If I remember correctly, yeah.
Okay.
just really curious question that can you Taylor expand around beta equals to 0?
You mean this?
This for this this distribution.
It should be, yes. I don't know.
but do you need to?
Yeah, because if I look at it quick, so if you do Taylor expansion, the first term you will get, you go beta, yeah, you will get infinity, right? Is it? No? Yeah, maybe, and then, yeah, because up there, you will get infinite, indefinite form somehow. Is it? Well, this is kind of basic math 101. Yeah, maybe. Yep.
In the numerator is e to the power of being 1 over beta squared.
This one, right?
Yes.
Yeah, beta square, right? Okay. Yeah, yes, beta square. Yeah, it should. I think it should get you finite value, right? According to the graph. So okay. สวัสดีจะถามมาเอาอะไร Yep.
I just want to be sure. If you use the Gaussian,
Yes.
there is one same.
Yep. But yeah, I mean,
Totally the same.
yeah, you mean the Gaussian distribution, right? Yeah. But you need a different trick of rescaling parameter in this Lagrangian here. Yeah. But you will get exactly the same. Yeah. It's really weird, but yeah, you will get the same. There is an online question. Oh my God. Okay. Okay. Yeah, the same. Let us assume upon you can upgrade non. How could this compatible? Is lambda a physical parameter in the end? Thank you very much, Hawaii, for these questions. Let me look at the first one first. What is the first one? Where is the, okay. Oh, where, it's too long. Where should I answer first? How could this be compatible with the earlier conclusion? Is lambda is a physical parameter in the end? The parameter lambda in this scenario, I would say, is somehow before we do the average. I mean, the metric is kind of the extra parameter that we have in the system. We know that actually there is it has the same unit with the velocity, but we don't know it is physical or what, we don't know. But what we realize that actually after we do the average thing, we need to pick the actually lambda is nothing but C/2. That's what we need to pick. It's kind of, I don't know. This is kind of what we get. But before we do the average thing, the parameter lambda is not necessarily to be physical parameter. You mean if you mention that physical, you mean the observable variable, right? I don't think so. Yeah, it can be. Yeah, I don't know what it is, but it has the same unit with the velocity. I'm not sure. This is answer your question. If not, then you can give me a direct message later, Hawaii. A second one is this is related to the question about distribution. Seem to get related to mechanics. One has to fine-tune the form of distribution. What would be the result if I say consider slightly the form version of your distribution? If I get your question correctly, yes, you actually, your question somehow related to the one that actually I put at the very end. That yes, of course, that we don't know yet. It might be a fact or it might not. I don't know. Yeah. And the last one, what would be the field theoretic version of? Yeah, there was in some other work. Actually, we we tried to construct that as well. Yeah. Thank you very much for the question, Hawaii. We can talk about this later if you still interested, or if you think I'm not answer your question yet, you can send me a direct message. Thank you very much. Yep.
Oh, okay. This might seem a silly question. Okay. I want to know if you could be able to go back after. No. I mean the Lagrangian that you did after many things that the relativistic emerge. Could you go back to the normal form at the end?
What do you mean by normal form? You mean
to be non-relativistic?
Yes, if you take the C to be like you take the limit on the C, right?
Okay.
Yeah, you will get the non-relativistic.
Okay.
back.
So what happened with the all the hierarchies, Lagrangians, in that sense?
Okay. You mean all this Lagrangian, right?
Yes.
It has, I would say that actually along the process, all of them has been consumed.
Consumed.
Okay. Yeah, have been consumed in the process, because if you look at where is it? I don't know. Maybe because here, because if you look at this expression here, every single L, I mean the infinite of them, has been consumed somehow in the process in order to get a nice and compact form here. Then it's kind of totally gone, right? And then you get something new here. I mean, the relativistic version of the Lagrangian out of this kind of, after you consume the standard Lagrangian and all the rest, which is actually non-standard Lagrangian that actually we get from the multiplicative one.
And then we get the non-relativistic limit. After
you mean after we get this one, right? Sure. Yeah, you can take the non-relativistic limit. Sorry, non-relativistic limit, and then you get back the standard.
Is it possible to take that limit in each hierarchy?
Interesting. We haven't tried that yet.
Okay.
Yeah, but yeah.
Because there must be leading order somehow, right?
Yes. Well, actually, the leading order is nothing but this here.
Okay.
I mean, the leading order actually coming out from the non-relativistic limit, right? Actually coming out from the nothing but the constant term. Actually, once you expand the, I would say, where is it? Once you expand, I mean, here if you do the series expansion, the first term is nothing but minus m lambda square.
Yeah.
Right. That would be the leading order of the non-relativistic limit. Is that answer your
Yes.
question? Okay. Okay.
Okay. I think it would be related to the question that someone asked.
How
So,
wide? Yep.
For the first one that he asked that is the lambda is okay at first the lambda is unphysical and then it turned to have some physical at the end.
Yeah.
So it would, I don't know, would be somehow related to like if it physical at the end, you can basically, in principle, you can add the dynamic term and make it to be dynamical fields in some sort, and this would give you like just to promote it as a dynamical field, and in such a way that it gives the lambda the more or less like the field content in so my idea is that you can add the dynamic term to the beta and make it dynamical in such a way that but at the probability that
you mean
that at the average that it come from like
you mean this one?
The beta one it seems undynamical at first, but in principle you can make it dynamical by adding like dynamic to the beta term. Like, my idea is it is like the axion field. It at first you make the couple to make the theta term where the theta is just merely the coupling constant in the CP violation problem. But you can make the theta term dynamical in such a way that it gives you the particle. You can allow you to interpret it at the particle, which is axion. You can do it in the same in your case for the beta to make it dynamical, and that would answer the first question that to make it physical.
Maybe, yeah. Okay. Very interesting.
I mean, it's not a question. I think maybe in principle you can make it physical in that way. That
I see.
That intentionally give it dynamics, so make it dynamical. But at the end, you expect that you give it dynamical, but at the end, the expectation that you need to follow the same pattern that you present here.
Yes.
Just a rough idea.
Yeah, I'm not sure that I get the whole point that you mentioned, but it sounds very interesting. Well, we can talk about this later. But I mean, what I would like to say is that we introduce the beta parameter into the system, and then we integrate them out, right? And then it's gone. I mean, at the very end somehow. I don't know. It might be. I don't know. But anyway, I don't know. But here, at this particular step, if you don't pick if you don't pick the lambda in this way, you can leave it in this way, and it can be anything, right? But if you pick lambda to be this kind of form, you get exactly relativistic version of the Lagrangian. That is the whole point. But actually, there is no constraint or no condition that actually your lambda has to be kind of c squared over 2. This is the way that we pick. If we pick in this way, we get relativistic version of Lagrangian. But if you leave it in this way, you will get what it is here. Anyway, but for the point of actually making beta to be like a dynamical variable, something like that, it's kind of very interesting. We can talk about that. Yeah.
Okay. Other questions? Okay. Okay. If we do not have other questions, I would like to say thank you for our speaker for an insightful and interesting talk today, and thank you everyone for participating this seminar, and stay tuned for the next seminar to come. Thank you.
Thank you very much.คือพี่ตอนนั้นพี่ก็เคย